Hi there. During this session I'm going to be talking about Coulombs Law. Coulombs Law was, discovered, unsurprisingly, by Charles Augustin de Coulomb, and used a device a little bit like the device we can see here. What we've got is a fibre which is able to rotate, but the amount of rotation allows you to work out how much force is being applied. He was also able to work out or measure the distance between two point particles, so Q1 and Q2, so using various forms of being able to charge these devices, he was able to work out how much charge was on particle Q1, how much charge was on particle Q2, and knowing the force or the resistive force which balanced that out, and the distance apart which the two objects became, he was able to develop Coulombs Law. Now, Coulombs Law stands like this. Force equals K, which is Coulombs Constant. I'll come back to that in a minute. Q1 times Q2, so this is the charge on the 2 points which are interacting, divided by r squared, which is the distance apart in meters. Now, Coulombs Constant is 8.9 times 10 to the 9 in a perfect vacuum. So that's my kind of big note. And this is why sometimes you might see in books a different value, is that sometimes this is calculated or is shown as what's known as the permittivity of constant of free space. So if we put that number in, the permittivity constant of free space is 8.85 times 10 to the minus 12. And if I put it into these calculations, it comes out with a value equal to K. As it happens, when epsilon is different to a vacuum, this just changes the overall constant, which rarely happens in physics questions, but normally happens in the real world. And that's the distinction you've got to remember. And as it happens, in the IB data booklet, F equals Q1 times Q2 divided by 4 pi epsilon 0 r squared is the value which is in the data booklet. So using this formula, gives you allows you to make some calculations. You've got to remember that the force due to two different charges has got direction. So sometimes you have to use vector addition. I'm going to describe this with an example. Here there's a question. The question basically says, what would be the resultant force on this particle here, Q1? Now, as we can see, there's a force of attraction between Q1 and Q4, and an equal force of attraction between Q1 and Q2, and there's a force of repulsion between Q1 and Q3, which gives us three forces. Now, in this situation, we're lucky, because as this force between Q1 and Q4 is equal in magnitude but at right angles to the force between 1 and 2, what we can do is we can work out the resultant force just by using Pythagoras. So what we have is the force squared plus the force squared, and the square root of that should equal the resultant force going at 45 degrees to those two forces. And in turn, once I know that value, I just need to subtract F between force 1, 3, between particles 1 and 3, and that gives me a final value of 118 newtons. So just be aware that you're going to have to think about vector addition in some situations, so you're just going to have to use some of the skills you've learned in the past. Let's practice with some examples now. So example 1, what is the force acts between two charges of plus 10 microcoulombs and minus 5 microcoulombs when separated by 10 centimeters? Things to be careful in this question are the positive and negative, the microcoulombs, make sure you get your standard index form correctly, and recognizing this is in centimeters and not in meters. Pause if you need to, try and complete the question. Now that you've done that, remembering that conversion Therefore, there's a force of attraction of 45 newtons. Now, that force of attraction means that the total force is a negative number. So rather than me saying the answer is minus 45 newtons, I've answered it in, therefore there's a force of attraction of 45 newtons. If we had a positive value coming out, then that would be a force of repulsion. So just be aware of that. Another example question. Now, looking at this problem, what you need to think about is the fact that there's two sets of forces, and we want to find the resultant force. Now, example A. Now, example A shows that there's a force clearly between position P and this positive value here, but there's no acknowledgement of the force of attraction due to this value here, which would be smaller because it's further away, but still there. The next one we look at, if I look at example C. Now here, if I look at, this is the total resultant force. So what I need to think about is that there's a force, a very small force, due to the positive value at the bottom right hand side, and a very big force to the more distant positively charged particle. Now that doesn't make any sense. We know that distance has an impact here, so the force should be greater towards the nearer value. And actually, for the same reason, that allows us to eliminate D. In this case, the resultant forces which would, or the forces which would create that resultant force would have to be exactly the same size. Still incorrect, meaning B is the correct answer. A couple more practice questions for you. I'll let you read these through. Pause. I'll come back in a moment and explain the answers. Now you've seen that, the answers are: force is 24 times larger, equals 480 newtons. The point to be careful here is that recognizing is that when the distance is halved, remember that it's an r squared factor. So that means actually the force is being multiplied by 4 times. And for the other calculation, it should come out as, and again, because these two forces are at right angles, we should have a resultant force which is 45 degrees away and is 13 times 10 to the 9 newtons. So there's some example questions, and that should help bring together everything you need to know about Coulomb.